Assalamualaikum and good day to all. So for today's lecture is about material indices, continue from the last week lecture. For today's lecture is about how to use the material indices in the material selection, where you start with the translating and deriving the index using design requirements. And then to derive the index, you need to know the function such as either mechanical or electrical or thermal properties. Also, you need to relate with the geometrical function so that it can tally with the objective and the constraints. From the design requirements table, we can get the function, objective, constraints, and free variables. In case for the function for tie in this figure, it relates with the tensile strength or yield strength. The objective is to minimize weight, so you will need to use the density in the index. Then the constraint will be the specific specified strength. Thus, for the material index, you will need to use the density divided by the yield strength so that you can minimize the density. Probably you can get confused whether material indices and performance indices are not the same thing, but it's actually is termed as the material performance indices. Okay, so it's the same thing. Okay, next. Two concepts are used in the selection procedure. The first one is the material performance index, which is the combination of materials properties that characterize the performance of a material in a given application. The second is the material selection charts, which are the plots of materials properties that form the maximizing factor. In the material performance indices, the performance of a component or structure is specified by three things. First is the function requirements, F, such as carry load, transmit energy, and store energy. Second is the geometry, G. Third is the material properties, M. So you have F, G, M. Thus, you can say that the performance P can be written as shown in the slide. Of course, over here is P, performance P, which is equivalent to function in bracket, functional requirements, F, geometric parameters, G, material properties, M. So, of course, you can relate with the other performance such as mass, volume, and cost. In many cases, the function, geometry, and materials properties are independent of each other and are said to be separable. That means you can separate this equation. Okay, so either you can choose over here or over here or over here. So you have actually three functions, F1, F2, and F3. So this means the optimum selection of a material is independent of the details of the design. Also, it is the same for all geometries and values of functional requirements. Thus, the performance P can be maximized by maximizing the function number 3, which is the material performance index. Okay, so this one you can optimize this one, then you can on overall optimize the other functions. In order to derive performance indices, you can see the procedure as below. Okay, first is to identify the attribute to be maximized or minimized. For example, to minimize weight, to minimize cost, to minimize energy, maximize stiffness, maximize strength, and maximize safety, and also minimize environmental damage. Second, develop an equation for this attribute in terms of the functional requirements, functional requirements, the geometry, and the material properties, which is the objective function. Third, identify the free, which is unspecified variables. Fourth, identify the constraints and then Rank them in order of importance. Fifth, develop the equations for the constraints. In this case, the equations are not related with shape. So there are methods to derive the performance indices, which is related to shape or non-related to shape. Six, substitute for the free variables from the constraints into the objective function. Seventh, group the variables into three groups, which is functional requirements F, geometry G, and material properties M. Thus, we can rewrite back into this equation of performance P, which is equivalent to function 1 for the function 2 for the geometry, and function 3 for the material properties. Okay. 8. Set the performance index in the form of quantity M to be either maximized or minimized. So we just need to use this third function F3 for the material properties index or material performance index. As you have learned in the strength of materials, the stress is calculated by dividing the force F with area A in order for you to get stress. With the increase of force, the length L will increase by delta L. Delta L is minimally, so it is very small, which is related to elasticity of the material. The material density will be the objective, which is to be minimizing the weight or minimize the mass, where you need to reduce weight while having a strong yield strength. Originally, density units is in kilogram per meter cubic or gram per centimeter cubic. Okay, of course, this one is in SI. Since you already have the cross-section area A and length L, you can calculate the mass by multiply it with the density rho. Okay, over here. This is called the objective function. Objective function, which is to reduce the mass or reduce the weight. The length L and force F are specified, and the radius R is free. The section must, however, be sufficient to carry the tensile load F, requiring that F divided by A, which is equivalent to fracture stress or fracture strength divided by section. Okay, also you can relate with the F divided by A, which is equivalent to yield strength, sigma Y. Okay, probably can get quite confused with this equation and how to derive this one. So let's see within the next slide. First, you have to understand that the objective is to reduce weight or to reduce mass. So the material index performance or material performance index is mass, M, small m. And then M, as you know, which is equivalent to area in centimeter, okay, in centimeter power of 2, multiplied by length cm, and multiplied by density rho, which is equivalent to gram per centimeter cubic. Okay, so over here you need to insert the fracture strength section equation, or you can include the yield strength equation over here. So by rearrange back this equation, finally you can get this kind of form. So over here is a separate thing. So this one is force and the length, which is we can separate it altogether. So all we need is just this item over here, which is the rho divided by the fracture stress or fracture strength, or rho divided by the yield strength. So in this case, the equation should be either minimize or maximize. In this case, the density increase, which is we not prefer. So the minimize of this function or the index will be the best. So in this case will be the minimize of this function or this index. We want to minimize the performance M while meeting the functional and geometric requirements. This means we want the smallest value of rho divided by fracture strength, or express them in a form which the maximum is sought. We therefore invert the material properties such as in this equation 3, okay, previously in the equation 3. So we can define the material index M as the largest value of fracture strength divided by rho. Okay, it's either one lah. Either you want to be it minimized or to be maximized. So to be minimized, the rho must be in the above, on the above of the fracture strength. Here is the detail step by step in deriving the performance indices in case for light and strong tie. Tie means pull like this. That is the meaning of tie. So over here the function is tie rod. Okay, as you already know, this one is similar as the previous example. Objective is to minimize M, and then the constraint will be length L is specified, must not fail under load F, and then adequate fracture toughness. This one is the constraint. Free variables, which is the material choice, and section area A. Okay, step 1, you need to identify the function, constraints, objective, and the free variables. And then step 2, you need to define the equation over here, which is the objective, so that you can get the performance equation. Then step 3, if the performance equation contains free variable other than material, identify the constraint that limits it. So you need to identify the constraints. For example, like this one. And then step 4, use this constraint over here, okay, to eliminate the free variable in the equations. So you don't want the free variable, which is A. Okay, section A, so that you can get these indices like this. And then step 5, read off the combination of material properties that maximize the performance. In this case, over here only. So finally, this is the performance index. Okay, simple. Now, to derive the performance indices in case for light, okay, lightweight, stiff tie. So the function is tie rod. The objective is to minimize mass, but the constraint is stiffness. So stiffness you need to relate with the modulus of elasticity or Young modulus. Of course, in case for this one, you need to rederive this equation for stiffness, which is S is equivalent to Young modulus multiplied by area divided by L. Okay, so the stiffness. Basically, you need to use the stiffness equation. And then replace this stiffness equation so that you can remove A from the equation and then to make it like this equation. Then you can choose the material with the smallest rho divided by Young modulus. Or otherwise, you can invert those equation or invert this uh, performance index into Young modulus divided by rho. Basically, it's just the same. Previously, you need to relate with the yield strength. Over here, you need to relate with stiffness. Here is the performance indices for weight in case for tie rod. Okay, over here you have the material properties such as cost, density, modulus, strength, endurance limit, thermal conductivity, thermal expansion coefficient. And then over here, okay, you need to refer either you want to use tension tie, bending beam, or bending panel. Okay. Next is to derive the performance indices for lightweight but stiff beam. So of course, minimize mass is the objective. So you rewrite back those equation. M is equivalent to area times length times density. But in this case, for the stiff beam, okay, you need to use the area which is B power of 2. I think you already know in the flexure strength. So stiffness in case for this beam, which is S is equivalent to C, okay, times E times I. I is the moment of inertia, second moment of inertia, moment of area, divided by length power of 3. Now you have to insert also this equation into this equation, and then re-derive back this equation with this equation. Okay, basically you have to use this stiffness and moment of area into the mass equation. So you just replace the area A with this one. Area A with the value of B over here. Okay. Then you can calculate or re-derive back the equation, and then this one will be the function which is related with the objective and also the geometry over here, which is related to material properties. So the material performance index will be the density divided by root, okay, square root of the Young modulus. So you need to choose the material with the smallest density divided by square root Young modulus. Next, for the lightweight and strong beam. So strong beam means that you need to relate with the yield strength. Okay, yield strength or fracture strength, either one is okay. So of course, minimize mass, derive by this equation. Okay, so that the constraint will be not fail under load F. So this is the constraint. So you need to derive the equation over here. M is the moment. So of course you already know this one is the flexural strength. Flexure strength, which is the yield strength over here, is the same. I is the second moment of area. It's supposed to be 1 over 12 times BH power of 3. But H is equivalent to B, so B power of 4 over here. Originally it should be like this, 1 over 12 BH power of 3. But B, which is equivalent to H originally, because this one is a square cross section. If not square, then you have to use BH power of 3. Now, once you have this equation all together with the yield strength equation, okay, yield strength, which is the flexural strength also, then we derive back and then remove all the constraint function over here, length and force over here, so that you can have the remaining material performance index. So in this case, you must choose the materials with the smallest density divided by yield strength over here. So this one is a 2/3 square root power of yield strength power of 2/3. So here is the performance indices for weight in case for beam. Okay. And then also you have the in case for the stiff panel, the method is the same. Okay. So you just need to replace this originally this equation I, which is equivalent to 12 of BH power of 3, where you have B is the width, H power of 3 is the height. So H is equivalent to T. Okay. Here B is the weight, width, sorry, and H is the, sorry, this one should be, H should be the height, which is the T. So you just derive back. Actually, you can just use this one. Okay. Then rederive back, rearrange this equation so that you can have the material performance index of density, which is divided by square root, e power of a third. Next is the light and strong panel. Okay, such as mentioned before, you just need to use this equation instead of b power of 4, right? Previously, if you have square cross section, then you use b power of 4 divided by 12. Over here is width times height power of 3. And then put it into the fractional strength or yield strength equation. And then put it into the mass equation. Rearrange back this equation. Then you can get this one. Okay. So this one is to minimize this part in case for panel. And then optimize selection using chart. So you can choose beam, minimum weight, stiffness specified, and minimize this one. So usually in the Granta EduPack or CES EduPack, you can choose like this. Okay. Also, you can relate with the performance indices in case for cost and energy. Just to mention that in order for you to reduce the cost, you can also reduce the weight. So weight of a material. So if you want to sell a material, so you sell it by weight. So the cost will increase as the weight increase. Okay, there's no such thing. The weight increase and the cost will be reduced. Okay, unless you consider it's a bulk selling or bulk sale. Over here, you can put over here CP, which is the cost per kilogram. So cost per kilogram need to be related with the density. Actually, this is 0. And then C is the unit in either currency, currency in ringgit Malaysia, in dollar, in pound, and so on. Okay, also you can relate it with the energy. So energy to process a material is related with the weight. The heavier or the higher the mass should be having higher energy. So for energy, just need to replace the density over here, rho, with Q rho. Q is the energy content per kilogram. Okay, table 5.5 over here is the example of material indices for different function, different objective, and constraints. So you can relate it all in this table. Actually, you can see it in the HB book. Right, I'm going to skip this slide because it is exactly the same explanation as before. Also this one. Okay, over here you need to do the screening, which is related to the constraints. So we suppose that the design impose limits on this of the Young modulus E, which is much more bigger compared to the 10 gigapascal, and the density need to be lesser than 3000 kilogram per meter cubic, as shown in this figure. So that means over here, in this figure, the Young modulus, which is need to be bigger than 10 gigapascal. So this line is 10 gigapascal, and then you need to have the density which is lesser than 3000 kilogram per meter cubic. So this one is estimately is the 3000. Okay, 3000 kilogram per meter cubic. So the optimizing search is restricted to the window box the limit. So you can select this region for the material. Okay. Next is to do ranking using indices on chart. So in this case, you can set the performance index M. Okay, over here, either you can choose yang modulus divided by rho, or over here, or over here. So that means in this case, the slope is 1, slope which is equivalent to 1. Here is 2, and here is 3. So this one is related to the previous two lecture. Okay, so you can start choosing by using the material performance index M. So in this case, you just use slope 1, which is less critical, slope 2 and slope 3, which is further constrict or further strictly the material is much more important in this case. Then you can use the design on the lightweight and stiff component as example over here. So you can choose all the materials that lie on the line of constants E power of 1 over 3 divided by density rho perform equally as well as a lightweight and stiff panel over here. So those above the line are better, and those which below this line is worse. So the figure shows a grid of lines corresponding to value of the material performance index, either having a slope of 3. Over here is 3. In case of this one, is slope is 3 from 0.2 to 5 in unit gigapascal power of 1 over 3. Okay, so over here. Next is the indices on the chart, which is you use the design for lightweight and stiff components. Okay, lightweight and stiff means that you need to use the guideline for Young modulus. Okay, and then you need to relate with the density rho. So the subset of materials with particularly good index value is identified by picking a line that isolates a search area containing a reasonable small number of candidates, okay, such as in this figure. So attributes limits can be added, narrowing the search window. For example, the Young modulus need to be much more bigger than 50 gigapascal as shown in the horizontal line over here, 50 gigapascal. Remember, this graph is in the log scale, in the logarithm scale. The materials lying in the search region must meet both criteria. So the first line over here and the second line is over here. So this one met both criteria. Their number is expanded or contracted by moving the index line up and down. Okay, moving this one, this line up and down, up here and down here. Okay. Okay, selection based on the index M, okay, which is equivalent to Young modulus power of 1 over 3 divided by rho, which is much more bigger compared to 2 gigapascal power of a third. Okay, megagram per meter cubic. Okay, together with the property limit of Young modulus bigger than 50 gigapascal, the number is expanded or contracted by moving the index line up and down. Next is the documentation. The list of the constraints usually contains some of that cannot be expressed as simple attribute limits. Many of these relate to the behavior of the material in a given environment, or to aspects of the ways in which the material can be shaped, joined, or finished. So such information can be found in the handbooks, manufacturer's data sheet, computer-based source, and many more. So here's example for the performance index for weight. For the simple exercise, identify the best material that's suitable to be used for light and strong tie. Okay, light and strong tie. So you need to use the CS EduPack, or you can have the Granta EduPack. So you can download the trial version for each of you. Okay. So just follow this step. Just follow this step. Okay. Using the software, you need to set the constraint attribute limits, which is the young models need to be much more bigger than 10 gigapascal, and the density need to be lower than 3000 kilogram per meter cubic. So no worries about this one. This one is only for the demonstration in the CES or Granta EduPack software. But in case for the actual test or actual assignment and examination, we will given you the list of material, and then the table, and the bubble chart as well. So you just need to draw the lines manually instead for this one. This one is actually you need to use it using the guideline automatically selected the suitable material. So the last step for the selection of the material is the ranking. So you just put the index on the charts. Okay, and then you need to put the documentation. Okay, shortly find the choice of material, which is identify 5 best materials. Of course, you have a lot of material that you can choose in this case in the software. So based on their material performance index M, so which of these will you choose, and you just need to put your justification why. Okay, here the summary and the conclusion for this lecture. So you just need to read it out loud by yourself. Okay, so next time we'll be discussing how to actually use the chart, the bubble chart, and then the material performance index line and so on, so that you actually know how to do it. Okay, thank you very much and have a good day.